Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone and welcome to IIT Madras. So today we are starting a 1 week GAN course titled Materials Informatics, Fingerprints, Graph Neural Networks and Transformer Based Models for Materials Design. We have with us Dr. Kamal Chaudhary, all the way from the US. He's from NIST. So thank you so much, Kamal, for taking out time and then flying so far for us. So I know Kamal from I think 6-7 years back, and we have been working together in this field. And it's a great pleasure to invite him here. And yeah, so I just wanted to give a little bit brief about what we are planning to do in the next 5 days or so. So every day we will have some lectures followed by hands-on tutorial. So both Kamal and I feel that in this particular domain, unless we go through hands-on session, we will still not be able to get up to speed. So that's why we have designed the course in this format of 50% lecture time and 50% of hands-on tutorials. And then in terms of the topics that we are covering, it's actually a very diverse range. Not only we are covering basics, so the first 1 or 2 days you will see it's a little bit grounded. We are covering basics, and then the third, fourth and fifth day we will actually accelerate quite a bit and then talk about some of the more recent advances that have happened in this area. So much more advanced architectures or models, we will cover those aspects as well. So our hope is that not only we are covering some basics, but we are also able to provide you some of the up-to-date models that have been developed in this area. So with this, let me invite Kamal again. Thank you so much, Kamal, for coming here, and the floor is yours. Yeah.
Thank you, Rohit, for this kind introduction and for the invitation. And thank you all for being here, leaving all your daily whatever you do at this time and investing your time on really exciting topic called materials informatics. So as Rohit mentioned, my name is Kamal Chaudhary. I'm a staff scientist at NIST for 9 years. If you're not familiar with NIST, National Institute of Standards and Technology, this is the oldest scientific lab in the United States, older than any national lab you can think of, and established in 1901. So there are 2 chapters of NIST, one in Maryland, Gaithersburg, and one in Boulder. And I'm from Maryland Center. We have around 4 Nobel laureates, and there are diverse research topics that NIST work on, and we as a team work on materials design aspect of it. And out of this material design, several projects has come off. For example, Materials Genome Initiative, and from the Materials Genome Initiative, one of the projects that I work on is called Jarvis project, which is available at jarvis.nist.gov. So for first few slides of my presentation, I'll go really basic stuff. So if you're expert, bear with me. If you're not expert, feel free to ask any detail level of question you want. So my goal is to take all of us together and on this exciting journey on materials informatics. And let's begin with this. So this is the overall outline of what we're going to learn in a few days. In the first day, day 1, as Rohit mentioned, we're going to learn about what are materials, what are types of materials, why do we need to classify materials, what is programming, what is classical and quantum mechanics, how does it help in modeling. And day 2, once we have gathered a lot of data from this either modeling or experiments, we can use something like AI ML techniques, different types of ML techniques to kind of find pattern in the data. And then in the third day, we go really fast, as Rohit mentioned, on deep learning models. So something like ChatGPT for material science and so on. So that will be the focus on the third day, for example. So hopefully with that, it gives you some outline. So get ready for this. So as we said, first day is just materials modeling and so on. So how many of us have done programming before, like Python, MATLAB or something? That's so wonderful to see. Most of you have done. So even if you have not done, it's not mandatory for this course. We will go really basic with the programming. So it's not necessary, but it's good to have that skill. So I'm pretty sure you have seen this kind of figure over and over if you are a material science major. How many for material science major? Please raise your hand. So a lot of you. Chemistry, physics, perfect. It's the right crowd to talk to. So material science, you will heard this, hear this kind of mantra. It's called PSPP, processing, structure, property, and performance relationship. So before we go there, let's talk about what is a material. A material is a substance, mixture of substance that forms an object. It can be pure, impure, it can be living or non-living. Okay, so it really covers almost everything. What is PSPP per se? So, it's kind of linking these kind of four paradigm of material design processing. For example, you want to have the methods and conditions under which the materials are produced. Take a simple example of cooking, right? So you have ingredients, you have processing, and your property is, is thick or not, or is thin or not, and the performance is whether it tastes good or not. If it doesn't taste good, then you have to go back to processing, structure, property, and so on. This is called material design in a way, in your kitchen. Something similar we want to do in our lab. So processing such as heat treatments like annealing, quenching. Suppose you are melting a metal and you suddenly quench it versus you slowly quench it. How does it affect the microstructure, atomic structure, and so on? It really affects the property and performance. So when I say the word structure, it might mean several things. It can mean atomic structure, like how atoms are organized. It can mean a microstructure, how grains are organized, and so on. So the structure is very important, and it of course depends on how do you process this. For example, grain size in metals controlled through rolling or milling. So here you are showing a nice movie, how we are doing the molding, and on your right hand side I'm showing you a diamond crystal structure. So for example, that is for silicon or so on, one of the most famous material, most useful material, and all of us have it. So this is how atomic structure looks like for silicon or diamond crystal structure. Now that was processing and structure. How about property? Now property means several things. That's very similar to what I said, the taste or something. It's like strength, ductility, elasticity, thermal conductivity, superconductivity. There are numerous property of materials. And performance of course depends on the property. For example, how a material behaves in real world conditions, the tensile test. You take a beam of rod and stretch it, right? Whether it's a nickel aluminum alloy or aluminum alloy or I don't know, wood will behave differently. So because it depends on this processing and structure. So anytime, any problem. So one of my professors, when I was learning material science, he had a joke that anytime you are asked a question in your exam and you don't know the answer, at least write these two things. First is PSPP. It has to do with any question in material science. You have to answer with PSPP and minimization of free energy. Somehow or other, these two will answer almost any question you have in material science. So it's very important to learn these basics. And this process of process, structure, property, performance is somehow called forward material design. There's also a phenomenon called inverse material design, where I want this performance. Can you tell me what property I would look for? What kind of structure would I look for? And what kind of processing would I do? So that is, this inverse process is kind of very new technique that we will learn as well. So we will learn both forward and inverse material design technique in this entire course. So this is a kind of very packed course. There are a lot of things to learn, and let's see how it goes. So I think most of us know this very famous person and one of the richest person, and he is probably the one person who suggested we do not need an university education and so on, might have heard, but he does recommend you should take Material Science 101 and you won't regret it. It's coming directly from one of the most influential character in our present generation, and that person is saying you should take material science. Not computer science, not biological science, but material science. It's that important. Now, there are different classes of materials. You might have heard from your school studies like metals, ceramics, polymer, composites. But why do we need to classify materials? Anyone would like to answer? Why would you need classification of materials?
Service conditions.
Service conditions. So application domain, right? So if you have something which requires ceramic application, for example, I don't know, this jar over there, you don't want to put in a polymer, like hot liquid or something. You don't want to put it there. It depends on the application. Also, it based on this classification, the property of the material depends on. If it's a metal, it's a ductile or something. It's a polymer, it's stretchable, and so on. So in a way, if you look around the universe, there's, I don't know, billions and trillions of atoms, different types of structure. And if you want to understand how universe work, or how your hand work or pen work, you have to understand what material is it made of, right? And for that, you have to really break it down, what components of this is metal and so on. And the more you can break it down, the more you can control it. And the more you can control it, the more you can commercialize it, good for economy and blah, 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 so on, right? So you will see in the materials informatics precisely what we are trying to do is distinguish one material from other. For example, fingerprint or descriptors. We'll learn about those kind of things. Like our signature, right? So we write your signature and my signature completely should be obviously different. So every material should have almost unique fingerprint, right? So this is similar. This is one of the first kind of classification or fingerprinting or signature of materials in terms of metal, ceramics, polymer, and composites. Now they can be solids, liquids, gas, crystalline, amorphous, and so on. So they can also be perfect and defect materials. So most of the materials in our real world scenario are defective, right? So it can be vacancy atoms where one of the point vacancies, such as vacancy where one of the atoms are missing, or multiple atoms are missing, or interstitial atoms, substitutional atoms where should be silicon, there's a nitrogen there, So these are all point defects. There can be line defects where a line of atoms are missing, like dislocation, or there can be surface defects like grain boundary, surface, and so on, right? And fun stuff start with defects, materials. So if you want to do materials modeling or material design, you should think about defects. Crystal systems. So similar idea of classification. Some people call it metal, ceramic, polymer, but no, I'm going to classify in the 7 classes: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. So we saw that silicon structure, right? How they have this kind of 3D structure. Like some of them have, they are characterized by the A, B, C lattice constants and the alpha, beta, gamma angles. And how do we have them? Whether A is equals to B equals to C, and alpha, beta, gamma is 90. That's cubic material like rock salt, and so on. And because based on this structure, again, the property will be decided. It's very important to understand the structure of the material, right? And so on. So how many of you have seen this kind of Bravais lattice and stuff? Please raise your hand. Almost all of you. So I don't need to spend too much time on this. So again, another way to say this is chemical bonding: ionic bonding, covalent bonding, metallic bonding, and van der Waals bonding. Now, ionic bonding, we know that there is a electrovalent bonding of oppositely charged ions, and covalent bonding, there is a sharing of electrons and so on. Metallic bond, we have metal clouds. Van der Waals bond, we have for example, van der Waals interaction. Now, why we need to learn this is, suppose we want to model this phenomenon, then we might need a kind of a universal model that can capture all this kind of bonding. It's extremely difficult, believe me. Like we have been trying to model all these materials from one model, one like unified model, is extremely difficult. One of the first model we probably learned is like Coulomb potential, Q1, Q2 over R, right? Charges are there and there's certain distance. So that's fine if you have like idealized argon gas or something like this, might work. But when you have sodium, chlorine, phosphorus 2 and something like this, at a different lattice, and what kind of bonding will be there is very hard to predict. There is no kind of general formula for this. What will happen if I have periodic table with 100 plus elements, if I take molybdenum, sulfur and something, I put it together in a certain lattice, what would be the property? There is no universal model like this which can do very, very fast and very, very efficiently. And this is why we need materials informatics. So we tried physics, chemistry, and so on. When it did not work, we tried physics to generate a lot of data and use something like machine learning to learn it. That's what material informatics in a way it is, right? All right. So we learned. I'm not going to go over what is metal, ceramics, polymer, and composite because you guys are already too smart for this. But I'm going to talk about this. We talked about characterizing material like property and performance. When we do this experimentally, there are multiple methods. For example, if you have a sample with centimeter to millimeter and micrometer, you are dealing with X-ray diffraction or X-ray fluorescence. When you have very, very small sample like atom probe tomography or Auger electron spectroscopy or scanning electron microscopy, scanning transmission electron microscopy, scanning tunneling microscopy, and there are many, many instruments, and almost all of them have like multiple Nobel Prizes, because they can actually, for X-ray diffraction, for example, I think have 10 Nobel Prizes. TEM, I think in 1980 or something, there was a Nobel Prize, multiple Nobel Prizes, because it gives you really a direct insight into what's going on in a matter, right? And this is really the overlapping area. And Raman of course came from this country, right? So really phenomenal method, and all of them have been used in conjunction with each other to kind of probe that material structure, property, performance, processing structure, property, performance relationship, and so on. So again, back to this. So out of all of this, we might in some of the tutorial later, we'll be using X-ray diffraction and TEM stuff a little bit in our later in our class. Yes. Y-axis is like parts per million. Like if you have like 100% of the sample versus 10% of the sample or something like this, how lower it can go. Like X-ray diffraction probably capture everything, right? It's like a beam coming in. But you have like TEM, you have like very small sample and focusing only on this.
Is it analogous to the interaction volume?
Kind of, yes. Interaction area and volume and so on. Yeah, good question. So this is, again, this is a representative chart. So don't take it like granted for everything. There are maybe 10 times, or not 10 times, maybe 5 times more of the experiments. But this kind of gives you insight of this. This is like a kind of huge data. And once you have this kind of experiment, you produce a lot and lot of data. And sometimes it becomes totally unmanageable to process this data as for like a 1 or 2 scientists. And that's another reason why we do materials informatics. So this is another way to look into the same picture where you can see some of the assemblies or components for naked eye, optical microscope, XRD, SEM, TEM, STM, and particle accelerator, and so on. So same picture within a different perspective. But what I would like to point here is, if you have a problem, suppose, and you want to know what is the best method I should use, that's why we introduced you this kind of all this gamut of methods, and then you select for your own application. So I wanted to show you this X-ray diffraction video, where you have a crystal, and then the X-rays coming in, and X-rays have a wavelength which is comparable to the lattice constant and bond length and so on. So it will go and makes distinctive pattern again for different crystal structure or proteins or macromolecules and so on, and that's becomes a signature of that material, right? And that's how you have a database of all known materials. And suppose you invented a new material, then what you do is just you will make this fingerprint using X-ray diffraction. You will not try to match with millions of material in the database. What you will do again is material informatics, where the computer will kind of search top 10 options, and the human being will select, okay, this matches this one, and this is the material. So this is again another application of X-ray diffraction. But to make that a million database or 100,000 material database, it took thousands of scientists' hard work, right? They created the sample, put in an ICDD data set or ICSD data set, and so on. So this is really like a huge effort, and I believe some of you might be able to contribute to this kind of work as well. All right, so we learned about characterizations using experiment, but why do we need modeling? What is a model, right? Why the hell do we need modeling? So what is a model? A simplified representation. It wants to simulate a complex phenomenon, because if you want to model, like if you want to do experiments on everything, it's too expensive, too resource consuming. So what we want is kind of a cheap and best kind of efficient process, and that is what model does. There are different types of models: physical models, mathematical models, statistical model, conceptual models, and computational models. We will be primarily dealing with computational models, where algorithms and simulation for studying complex systems and behavior. Okay. We are not doing, for example, the mathematical models. Well, these are the part of materials informatics, but we will be primarily focusing on the computational models. Now, in terms of modeling, what kind of equations are we solving, right? So it depends, again, what is the problem you're trying to solve. If you are trying to solve, in the x-axis you have the mass, and y-axis is the velocity, and c is the velocity of light, of course. If you have a system, if you have a problem that depends on very small mass and very small velocity, very less velocity, you can use Schrodinger equation, which solves, for example, electrons and so on. And if you have a bigger mass, like a football or something like this, you use Newtonian equation. Usually we deal with Schrodinger equation and Newton equation. Rarely we use Dirac equation, where we have high velocity and low mass, right? Like core electrons, like hadron and all these kind of things. We don't need that unless you are dealing with like spin orbit coupling effect or something like this. We don't need that. Einstein equation is different level, and that becomes relativistic, of course, where we have ions in cyclotron. We probably don't need that either too much. So we will be primarily focusing on Schrodinger equation and Newton's equation, and based on this, we can classify different types of modeling methods. So when we have a problem, suppose there is failure in a component, I want to model this. Which method should I choose, classical or quantum? So that depends. Sometimes we need a combination of this. So what does multi-scale modeling offers for us is kind of integrates this kind of quantum, classical, and so on in one picture, or at least try to put in one paradigm and infrastructure to answer our questions. It can be from quantum mechanics where we are dealing with electrons, and there are many methods in quantum mechanics. One of the most famous method is density functional theory, DFT. How many of you have run DFT simulation? Look at this, perfect. So there are different software, Quantum Espresso, VAST, GPaw, Abinit, and so on. Similarly, there are molecular dynamics where we are solving Newtonian equation, and instead of dealing with electrons, we are dealing with atoms, and there are other software like LAMMPS. GROMACS is good for like modeling proteins, viruses, and so on. I promise I didn't touch this. Anyway, mesoscale modeling, where we are dealing with microstructures like MOOS, PRISM FF. Finite element modeling, which is very popular in industrial applications, where we try to model processes, deformations, and heat transfer, and software like Phoenix, ANSYS, and SPIFI might help you with this. So any questions so far? Is it clear? Yeah, okay. So this is a nice picture that I personally like on, again, yes? Yes. So yeah, so molecular dynamics is the method, and force field is kind of its ingredient, like component. So without force field or interatomic potential, you cannot relearn molecular dynamics. So sometimes they are used interchangeably, but yeah, kind of force field is molecular dynamics is a superset of all the force field in a way. Yeah.
So where does Monte Carlo come in?
So Monte Carlo depends. It might be between quantum mechanics and molecular dynamics in between, or molecular dynamics and mesoscale in between, because you take information, for example, from DFT or MD and try to model the next step in kinetic behavior and so on. So again, this kind of like Monte Carlo is a good example. Machine learning is also a good example. It can work on multiple scale. You can do machine learning for finite element, DFT data, MD data. So it's like it's also kind of integrated in a way as well. There can be molecular dynamics using quantum mechanics like DFT MD, right? So this is not kind of separate island in a way. They are all linked together. So yeah, as we are saying this, based on time scale and length scale, we have ab initio, atomistic, coarse grained modeling, lipid modeling, and so on, finite element modeling. Like again, this depends on structural materials. If you are from electronics background, you might look differently. For example, solving green functions, Kubo function, Kubo equations, or drift diffusion equations at different level, like what is used for semiconductor electronics. You won't use. So the word multi-scale modeling is kind of different and different aspect in a way, right? Okay, I'm going to use some water. What do you think? Too much is helping, or do you think it's too much boring stuff? What do you think? It's good? Good, okay. How many of you have done MD simulations before? Can you run? Yeah, please, yeah. Good, so sufficient amount. So, sorry? Yes. Green functions are very generalized techniques. It doesn't have to be only for partial differential equation. So green functions are also used for autocorrelation function, and when you do like molecular dynamics to get thermal conductivity or phonons, they are also used for solving like excited states in density functional theory. So like how one orbital is related to another based on the relaxation time and so on. So these green functions is kind of a tool. same as AI ML is also a tool. It's a generalized framework. Yeah. Maybe I should make a picture of what is different between a method and a tool. So just, and they kind of are used interchangeably, but they are distinction at the same time they are similarity. So don't confuse with them with each other. Hope that answers your question. Yeah. So yeah, green function is a really powerful technique. It's used for many things, astrophysics and so on, a lot of things. These are some of the books for multi-skill modeling. And for example, the first one I think is publicly available. So you can also get it if you search for fundamentals of multi-skill modeling. It's a nice overview of all kind of methods like DFT, MD, finite element and so on. I don't think it talks too much about machine learning, but it has some part to it. Because the field is so evolving so fast, it's hard to keep track. So I personally, what I do is review papers and stuff, like recent advances of I don't know, machine learning and material science and so on. So those are somehow more informative than books, but books are good to get started, for example. So now we come to the other part, which is programming, because we are talking about informatics, information and so on. We need programming. So again, this, some of you might have heard this over and over, but I'm going to just go over this. So what is programming? Computers, see, do not understand physics, they do not understand chemistry, maths, they do not understand what they understand in numbers, 1, 0 and so on, right? So how do we convert our sophisticated information from physics, chemistry and so on in a way that can be converted to 1, 0? That's what the role of kind of programming is in a layman word, right? And there can be different kind of programming languages. I'm sure some of you might be familiar with this, like high level language, low level language, syntax, semantics, static and dynamic typing, compiled versus interpreted. There are different types of programming languages. In material science, I feel like if you are doing something like core development of methods like in DFT or MD, then we'll be using something like C, C++, Fortran. But if you are using some sort of guiding data, then you'll be using like Python, Julia is pretty nice nowadays, what else? Rust is good, Go is good and so on. But Python is probably most popular in terms of materials informatics and so on. I'm not progressing the slides, but it's just, I don't know, it's like you're talking too much, move on. So again, programming is pretty popular, so I don't need to introduce to you who this guy is. So when I was in grad school, I saw this, this pamphlet, and I was like, okay, I'm in good boat, you know. So a few years from now, and from kindergarten and so on, they will be learning programming, right? And there have been also some attempt that programming won't be necessary. You just use English text, like what you want to do, and to write the program for you, like GPT model and so on. But eventually, one way or other, it is very important and very good skill to learn programming, because I feel like it helps me to figure out the algorithm that I want to solve a problem, right? So it's a very good technique under the belt. Whether you are an experimentalist or you are a theoretician, doesn't matter. In a way, it's a good way to learn as a skill. So we will go through some of the basics of programming using Python and so on, because I don't know how some of you might be too much familiar with programming, some of you might not be. So so for example, you're learning a language, you might have to learn some basics. Let's see if this works. Okay. For example, what is variables, data types, loops, function, list, you know. If you are advanced, you might need generators, list, regex is pretty good, lambda functions. If you are working on, once you have made the model and you want to share with the world, you might have to make an app, right? And nowadays there's multiple apps like Django, Flask, Fast API. If you are doing something like object-oriented programming, where you use programming method as a template and put the data there and use it in a different way, but the template is the same, that's called object-oriented programming. How to install packages and stuff. If you work with programming, it's a nightmare sometimes to deal with conflict of programming packages and stuff. So what's the best way to reproducibly install software, work with it, so that you work from now and 2 years from now it will still work and not it fails. So that's kind of package managing, arrays, you know, and recursion and so on. File system, whether you store data in CSV file or whether you should store in JSON file, HDF file, because it's fine if you have small amount of data, but when you do experiments or simulation, you have terabytes and petabytes of data. So what's the best way to store them? What's the best way to access them? That's why you need some kind of file manipulation. Unit testing is, for example, remember when we do some kind of test programming, we check whether it works or not, right? And over the year, over the time, it should keep working. It's not fail. So that's the role of PyTest or testing. So it's kind of every night or every few days, it automatically kind of tests the programs you wrote using something called GitHub Actions or GitLab Actions. We'll probably learn a little bit about this. And this is very important for if you are doing a long-term project or if you have a company and so on. So if you have a product, and suppose your product works very nicely today, and 2 days from now there's a new NumPy version, everything fails, that will jeopardize your whole company, and there will be a huge loss. So how can we make this testing kind of more robust, reproducible, reusable? That's why testing is important. And data science like Matplotlib, PyTorch is very popular. TensorFlow used to be popular from Google, but now not too much. Scikit-learn is probably one of the most used machine learning tool, especially for classical machine learning. So when I say classical machine learning, what I mean by this, where you give fingerprints or descriptor to the computer, and deep learning is where you don't necessarily give that. It's try to figure out from itself. So that's one of the kind of vague distinction. So yeah, these are some of the tools and techniques for programming. So let me go over briefly. Let's see how we are doing with this time. So I'm supposed to keep going until 11, I believe. Okay. So data structures is very important. So I teach this kind of course in Johns Hopkins University, and there's a mixed crowd, right? So I start with what are variables. So there are a lot of funny story, but I'll not go into this. But you should understand what are the variable types, like is it integer versus float or character, string, and so on. So you'll see that as a kind of side story, there have been a lot of machine learning models, for example, which have billions of parameters, right? And you cannot store them as floating numbers, like which has certain number of bytes. So what they start doing is they start thinking of a method where you can store floating point into integer format to save the memory, or integer into string format, and so on. And there's a whole game of machine learning. For some class of machine learning is just this: how can you deal with this kind of data? So variables, though it looks very simple, is very important to understand the variable types. Like if you have shaft speed 1200, it's an integer, but 1200.0 then it becomes float, right? And when we do something like machine learning, what is the level of precision we want? Like 16 digits, 64 digits? I don't know what's the level of precision we want, and it depends. So it's very important to know the variable types. Arrays and list. So when you have multiple of these variables, we store in arrays, like forces, resultant forces, and one of the packages is called NumPy, very popular in Python. So here is a force magnitudes. Anyone who has not used NumPy, please raise your hand. 2 people. Okay. So it's kind of umbrella package to manipulate different type of variable types, different type of character types, floating types, and so on in one format. And it gives you a lot of helpful function, like if you want to sum this number, right? In old days, we have to write a code that for loop and just sum it and stuff. Now we don't have to do that. We just do np.sum, and here is the thing. And not just sum, many like integration, differentiation, all of these are well built. And one of the reason why this programming languages such as Python become so much popular, because of these inbuilt functions. And also they are very, very efficient. So yeah, so these are arrays and list, and we can also have arrays which have same data types, and list where we have different data types. So for example, steel is a string, okay, this is a integer, this is a dictionary, Python dictionary, and you can have mixed data types in a list. Okay, so you can also store that. Sets, where you have for example different combination and you want to get unique parts. Dictionaries, these dictionaries are pretty important for materials informatics, where you have not just Excel sheets. Suppose you have a data and you cannot just have a tabular data. Sometimes you have a data of data, and some of them have it, some of them do not have it. So how to store this kind of non-tabular data sets and stuff, So that's where dictionaries come into play. So you have, for example, material property, and under the material property there is a dictionary called and the dictionary is defined by key value pair. So here key is steel, and the value is again another dictionary which has key as density and value as this, key as Young modulus and value as this, and so on. And you can have nested dictionaries, right? So the good thing is, in old days where there was no dictionary, people, suppose you want to find the density of steel, people would write a for loop and go where there's a steel and another for loop to get density, and that will get, it's very, very slow process. Now you'll just do steel is material properties, steel and density, and you'll get the number, right? So it's very much useful for something called Mongo database and stuff. So it's probably for this class it doesn't matter, because we are still learning new things and dealing with small amount of data set. When you have Instagram kind of data, you know, or Twitter kind of data, it's really humongous. And for this, there's only maybe 10 scientists over there. So they really have to be efficient. How do you tackle this data? And people who can tackle it get really paid very high. So you have to be very efficient with dealing with this kind of data structures. And also there are a lot of research about this, how to store this kind of data. And data handling, so most of you have heard or used Excel sheet. There's a JSON file, and there are multiple programming languages like Python, and there's another programming language like MATLAB. It used to be popular, then Python came, and MATLAB, because it's kind of commercial, and Python becomes open source, and it becomes more popular, and so on, right? We talked about object-oriented programming. So where it is objects here are data structure consisting of data fields and methods. So let me explain this. What is data structure in terms of methods and inheritance and so on. Suppose we have a object called, which is represented by the word class, machine component. Now machine component can be characterized by initializing this function called material, like it can be aluminum, silicon, or whatever. Now there can be function called def, which is display material. Now you'll ask self. Self is kind of the object, you see. So self becomes the template of this. So you can have multiple type of material stored in this format. And if you ask for machine component dot material, it will always be this data. So you don't have to store in Excel sheet and stuff. And that's the example of a class. Now you can have inheritance. What I mean by inheritance, you can have another object called bearing, which is a kind of a subclass of machine component. So when you do this, you not just get the variables of this part, but also from the previous part. So you kind of get it for free. And in a way, you have to use, it saves a lot of programming time and storing time and so on. And that's why object-oriented programming are very, very popular. So yeah, we can call it a template or blueprint, and it's defined by in terms of data attributes. Like these are all the self dot something is data attributes, and behavior or methods, like all the definitions or something like this you can call it. Now whenever we use in material informatics like atomic structure, we work with something called schema. Like when I say material, what do I mean by this? Atomic structure. By atomic structure, for example, we have atomic coordinates in XYZ. What are the atomic elements like aluminum, silicon, and so on. So this becomes a kind of a blueprint of atomic structure. Similarly, if you have to make a blueprint for microstructure, for example, what's the domain size, what is the SEM image, or the TEM image, for example, and that becomes a blueprint. And there, believe me or not, there's a huge research called ontology research in materials informatics, and their whole job is just to figure out what's the best way to represent a particular class of material, a particular method, a particular experiment, and so on. Not too much metadata, not too much information, not too less information. What the sweet spot of that? And that's where object-oriented programming becomes very, very important. So def is fine when you work with like beginner level Python and stuff, and when you become super smart, then you start doing a lot of classes. Okay, parallel and high performance computing. May I ask how many of you have run a job on a computer cluster, like high performance computing cluster? Maybe some of you. So you are aware that there are some stuff you can do on your mobile phone, on your laptop. There are some stuff you cannot do on your mobile phone, laptop, and that's why we need high performance computing infrastructure. They have many cores, GPUs, shared resources like storage and so on. Sometimes there are support system. Suppose something doesn't work, you don't have to like bang your head on the wall, but just write a ticket, and there's a nice guy sitting over there, they'll answer your question, right? So that's the role of HPC, right? And it also provides data parallelization, task parallelization. Suppose you want to calculate the atoms in the universe or something like this. You probably have to do it parallelly. You cannot do one by one, right? So something like this, we can be parallelized, multitasking in a way. Parallel algorithms are there. So you might have heard of the company called NVIDIA, right? For one of the richest company now. So I don't think many people know how does GPU works in terms of programming or parallelization, because this is their patented secret sauce. So if you can come up with something which can be much more parallelized and efficient than the NVIDIA, then you might be the next billionaire. Okay, that's where the information science is. So just if something works in your cluster or computer, just don't take it for granted, you know, and always do scaling studies. Like if I have a molecular dynamics method, for example, how does it scale with the number of atoms? 10 atoms, 100 atoms, 1,000 atoms, million atoms. Is it linear? Is it, you know, quadratic, exponential? Obviously, what should be linear is the best, right? But again, you will see that probably in some of the examples, this is not always the case. Sometimes life is not that simple. Life is not linear. So then we have to use parallel algorithm to make it simple, right? Multitasking. So and CUDA is compute unified device architecture, is a parallel computing platform, and it's really popular. I saw somewhere a news on Twitter that some high school student or undergrad student from Carnegie Mellon University, he has a code called Tiny GPU. So whatever NVIDIA did in years, this guy bought a GPU, locked himself in garage for a few days, covered what's going on, and made it open source in a way, and everybody started looking at it. So see, because he did not stop, like, okay, this is working, I'm going to stop there. He kind of wanted to go into this, right? And that makes him unique. So again, this is where the specialization comes into play, where you don't take things for granted. So when we are learning materials informatics, we'll be learning about databases, fingerprints. Keep asking why, and how can we do it better, and so on. And that's what will make you as a scientist or as a researcher or an engineer as a unique person, right? So again, so parallel and high performance computing. So there are different ways to code when you have simple, like for example, you want to calculate a factorial, simple thing. We have done it over years and years. You have a number like 5, 7, and so on, and you want to calculate the factorials. You can have a function called math.factorial, which is an inbuilt function, and you can loop over all the numbers, and this function is calling this function, for example, this serial factorial. And but if you do in parallel language, you have to use something called multiprocessing in Python, called pool. And there you will see they are using two workers in parallel, which is calling this function called compute factorial, and then at the end they join these results. So kind of have multiple slaves work for you, and there's parallel processing. Sometimes it is efficient when you have a lot of data. For low amount of data, sometimes it's not efficient. So keep an eye. It doesn't have to be always efficient. This multiprocessing tool. Where are we? Okay, yeah. And same with parallel and high performance computing. So suppose you have to write a code to do a square, just a number squared. You can, in Python, you can write this function called data **2, which is power of 2. But if you want to write for GPU, you have to write this ugly looking code, where you have to write something like C++ language, a machine level kind of language. And then it can be compiled on GPU, and then you can be very efficient if you want to compute numbers. I don't think we'll have time to go over that part, but I do have a notebook on Jarvis Tools notebook we'll share with you that compares the CPU and GPU of computing squares. So again, we have not got into materials informatics yet. We are still dealing with computing and stuff. Although it seems like a tangential topic, but extremely important when you have larger systems to simulate and so on. So we have heard about quantum mechanics. I saw a kid, 3 years old, he can say H psi equals to E psi, 3-year-old kid. So it's very popular nowadays. But it is very fascinating even to date what is quantum mechanics is. It's in classical mechanics where everything is deterministic, here things are not deterministic, and we are dealing with, remember with the previous slide, dealing with very small mass and very high velocity, or relatively high velocity at non-relativistic level. And for this there was a Nobel Prize for Schrödinger in 1933, and anytime you have a problem, if you can somehow write its Hamiltonian operator, then you probably have solved the problem, but it's very difficult to come with the Hamiltonian operator. We'll talk about this, how to take the Schrödinger equation in a more manageable way. So when quantum mechanics came, we talked about this picture, I think, already. So we're dealing with Schrödinger equation. So again, quantum mechanics is extremely hard if you want to learn everything, right? And there was a famous joke or a comment by Richard Feynman that anyone who claims to understand quantum theory is either lying or crazy. So it's never like this. And this was more funny. Somebody saw quantum physics in one lesson. He's very happy. Oh, I'm going to learn in one lesson. But he saw the hours, and they're like, oh my god. So it's not that easy. So what you have to do is, again, the problem solving strategy. What is the problem we are trying to solve? Anytime you have materials informatics or so on, always think about the problem. You should be very, very clear. Else you'll be lost in multiple rabbit holes, we call it, right? So unfortunately, we won't be able to play this video because I don't know how to do this. Anyways, but there's a nice video on YouTube which shows about wave particle duality. So which is a fundamental aspect of quantum mechanics, and it describes how every particular quantum entity can exhibit both particle-like and wave-like behavior. And one of the most famous example is double slit experiment. So for example, light, right? And light is a broad term, but a visible light behave as a wave, and it creates an interference pattern. So in this video on YouTube, you will see that when in this picture, the light is behaving as a particle, and then it's give a pattern, and it also behaves as a wave, and then there's an inference, there's a constructive inference, destructive inference, and it gives a certain picture. And based on this, there have been several experiments like X-ray diffraction and so on. Most of this is based on this wave particle duality. So very realistic application of how quantum mechanics work. So it's, unfortunately, I didn't. I was not able to play this video, but if you
pressing Control B.
Control what?
Control B.
B. I tried, didn't work. I don't want to mess it up, so I'm gonna keep it that way. Okay, so but go to YouTube and search for wave particle duality. Data Burger. There's a company, in French company called Data Burger. Okay, and they have nice tutorials like this, a lot of videos. Okay, so quantum mechanics in a more manageable way was managed by these two gentlemen, Walter Kohn and John Pople, for which they got Nobel Prize in 1998. And what they did is very interesting. So in quantum mechanics, remember we have h psi equals to e psi. So psi is the called wave function, and h is the Hamiltonian, e is the eigenvalue. What these two gentlemen said, instead of dealing with psi, which is a very complicated quantity, we will be dealing with electron density, or psi square, and that makes the problem more manageable. It sounds very simple, but that was a remarkable achievement, and for this they got the Nobel Prize. And there is for a paper called inhomogeneous electron gas, Hohenberg-Kohn theorem, and so on. Unfortunately, I won't go into Hohenberg-Kohn theorem and so on, but I would, if you want to look into it, it's a very fascinating topic. So I had a chance to meet with Walter Kohn when I was in grad school. He was at UC Santa Barbara, and I was doing my PhD and stuff. So I remember he's not anymore, but he was 93-year-old when I met him, 93, and still active like a grad student, very, very active. Like these people are all the Nobel laureates I have met. They are very, very inquisitive people. I don't know about knowledge, but they want to know everything in the world. So I was thinking I will ask him question, but he was asking question to me about quantum mechanics. Like, what are you talking about? So they are very, very inquisitive people. And one thing they were very interesting in this density functional theory is, first of all, they deal with a fictitious system called Kohn-Sham system of non-interacting particles. Suppose you have psi, which is a wave function of multiple electrons. If you have a salt, right, table salt, there are many, many electrons there. If you want to solve the psi for each electron, it becomes really an unmanageable problem. So what we do is like we assume that there is a field, a constant field, and each electron is seeing that field. So we will do only kind of two-body problem in a way, effectively, or one particle problem. So that's what this fictitious Kohn-Sham system does, and it uses density chi square instead of wave function. and it converts this H psi is equals to E psi into this format where we have the effective potential, and here we have eigenenergy for each I here is the particle, and you can break down the effective part into 4 components: kinetic energy, nucleus electron interaction, electron interaction, and something which doesn't work called exchange correlation. Whatever doesn't work, just throw it there, called exchange correlation. So that was also a magic thing. So one of the Kohn-Sham theorem is we do not know what exchange correlation is, so we are going to use something called variational principle, and to kind of try it multiple way and minimize the energy to get exchange correlation. So again, we will not go into exchange correlation, but at least this part is clear. What is kinetic energy? So we have electrons, right, and they are moving very, very fast, right. So we get the electron kinetic energy, nucleus and electron interaction, electron interaction, and so on. So although it is a complete theory, there are several approximations. For example, when you are solving this partial differential equation, this is what it is in a way, solving partial differential equation. We have to take a grid, right. How fine is your grid depends, based on this you will have different solutions. So K points or that grid points are very important. If it's not very good, you will not get good results. And if you do machine learning on this garbage data, of course you will get a garbage output. So what I want to bring out is like how you get the data is very, very important. And most of the work goes in getting high quality diverse data. That's if you want to make a name in the materials informatics field and so on, think about the quality of data, make your own data set if possible using experiment or theory, and make it high quality. Then people will use this data and cite you, and then you'll have thousands of citations. So that's how the pipeline goes. Think about the yes. So on the third day I talk about something called quality of data. So but you asked now, well, I'll talk about this. So one of the thing is called ground truth. What is ground truth? So for example, for DFT, the ground truth is experimental data. So what we do is like the textbook have a lot of like bulk modulus, elastic constant, band gap, all those things, and we compare with our DFT numbers with that number, right? And then we say, okay, this works for 100 materials. Now hopefully it will work for other materials too. So that's how we kind of benchmark this existing or new data with experiments. Now sometimes we don't have experimental data. So what we do is high fidelity quantum mechanical calculation, like couple cluster theory, couple cluster theory with triplets, you know, many body theory and so on, and that then we compare DFT data or MD data to that data, and then we call that as a high quality data. So again, if you do hearty like many body theory for many materials, it will be very time consuming. So we have to find some sweet spot, like find out this method works for this class of material and not for this class of material. So even if you don't have very high quality data, but you can know a priori that what is the limitations of data, that is also very good. That gives you a green sign. Also, it should be variable data. Suppose I have seen some machine learning which is working only on graphenes, like 1 million STM images of graphene, and that's all it is, right? Graphene with this defect, that processing time combination. But if you have a trained model on graphene, and suddenly if you have phosphine, then it will not work. So you should have so what is the word? Yes, exactly that word. There are 3 V's: veracity, versatility. There are few terms there. So it should be diverse data, and it should be well curated data. In a way, it should be easy to access. Not just you put something in zip file and only you can use it and rest of the world cannot. So that also usability is data is very important. So one of the reason you will see that Jarvis got so popular because compared to any other data set out there, there are many other data set, but it's so difficult to work with. So people by tendency they use something easy, right? So that also makes a data quality better or worse based on usability. So usability, variability, versatility, veracity, those are the factors of a data set that makes it kind of a good data set. Yeah, hopefully that's one of the answer. So again, key points: van der Waals interaction, whether you have kinetic energy derivative, whether we have sometimes relativistic information in your DFT method or not, and for example, you have electron-phonon coupling or not. So those are very sophisticated things. But what I want to point is DFT is not one thing. It's not something you can buy in Walmart. You know, what's the Instamart here, right? What's the shopping store here? Instamart? Which one? DMart, yeah. It's not something you can just go and buy in DMart. It comes with several kind of factorization or characterizations, sophisticated like specification and so on. So you always have to report whenever you have a DFT data set with what specification you did that. All right. So I'll not go into exchange correlation, but exchange we have is two electrons with same spin cannot occupy the same spatial position, like Pauli exclusion principle and stuff. And correlation is motion of one electron in a system is correlated with motion of all electrons. So this is not classical picture. So if you have an atom here and one atom at the end of the universe, classically they should not be entangled or they not be related, but they are. When they are like very small mass and very small velocity, they are entangled or they are correlated. So nobody knows, I think, how in materials this exchange and correlation, what's the functional form for this? Nobody knows that. If you do it, you'll get a Nobel Prize, I feel like. So, but because we don't know this, we have to use this variational principle to solve DFT equations, kind of trial and error. And there are several approximations for this. One of the most earliest and still most popular is LDA, local density approximation. So when I teach at Johns Hopkins, one of the homework I gave them is just write LDA from scratch. So although sometimes they cannot do it from scratch, I give them partial points. But the process of thinking how you can take electrons as a gas and from their perspective, you use something called Thomas Fermi model. You might have heard from long years ago, and how from there you can get an approximated electron-electron exchange correlation that will give you LDA. Now that's based on density of the cloud or density of the electrons, but sometimes the gradient of the density is important. How fast or how slowly is varying, that gives you generalized gradient approximation, GGA. Sometimes we have to solve something called Hardy-Fock theory equation, and from there we have to make something called exchange that we talked about, and we have GGA plus that exchange, that gives you hybrid functional, which are more time consuming but more accurate. So one of the major kind of known problem in DFT is it's known to underestimate electronic band gap of materials. So again, this depends on what kind of functional you are using, what kind of approximation you are using. If you use hybrid functional, you might get better band gaps, right? So again, that again comes to the question of data. A lot of people are doing machine learning on garbage data, which is LDA or GGA data. So of course, the model will come out is garbage model, but the idea is it gives you a kind of a guess, kind of initial guess. So you don't take it for granted for real. It just gives you identify trends, and then you kind of go from there experimentally. So this is how DFT kind of works. You have suppose you have silicon or aluminum or argon gas. So you can assume what's the number of valence electrons you have, right? And where they are situated in the L, you remember Bohr's model, K, L, M, all those things. So you make an initial guess. This is the argon gas atom, this is the argon atom, and this is the electron cloud. Now I'm going to mix them, okay, and mix them in a way that minimizes the energy. Remember I talked about minimization of free energy. So I'll try to minimize this. First, I'll calculate the interaction using something like Q1, Q2 over R kind of thing. But there are some more terms: external potential, Hardy potential, and then put in the Korn-Sham equation. And for each orbitals like K, L, M, we are the psi I is that we are solving for each of them, and we calculate the density. And from the density, the Hohenberg-Kohn theorem says if you know the density, you know the energy. So we'll try to get the energy from there, and we will see that if you have a trial density, this is my energy. There's another trial density. There's this energy. So I'm going to take this energy, and then again I'll feed back to the initial step and keep doing iteratively. If by anyhow, if you knew what this exchange correlation is, then we don't have to do all of this, and then it will be super fast. But again, nobody knows this. So this is why the problem is there. And once you know the energy, you can get dy dx. Remember the derivative with respect to the position, and that will give you forces. From derivative of forces, you get phonons. From derivative of phonons, you get thermal conductivity. From derivative of thermal conductivity, you get something like Grunizen parameter. So you can, once you have the energy kind of quantity, you can get all this sophisticated information, and again it goes back to structure property performance relationship. So that's how it helps. And again, this is one of the example code I again ask students to write, because people use DFT code so much, WASP and what's the name, Quantum Espresso and stuff. They never know what's going on in the black box. So, it is good to have even for 1D Schrodinger equation or 1D system of gas right from your own, and then it will help you, like if you are doing machine learning or something like this. There are people who are kind of running this kind of running toy models, right? So, first you try to solve using this iterative method, and then you say I wrote a machine learning model that can take initial guess and give me final without doing any iterations. So, it expedites, accelerates the process. So, there are machine learning process for these. So, yeah, so whenever there is a problem which cannot be solved analytically, machine learning is extremely very helpful. So, in a way that can also be a guiding principle. So, in a DFT calculation and so on, so 9:30, 10:30, I have 30 more minutes. Okay. So, we have to set up a system. So, how do you set up a system, right? Remember, we cannot do processing in modeling. There are some processing models, but not too many. We have to get structure. So, these structures comes from something like NMR spectra, X-ray diffraction spectra, and so on, and that gives you the atomic structure. So, again, there have been several Nobel Prizes, like in 1951 or something like this. There was a DNA double helix structure and so on. So, that gives the atomic structure. Ribosome, I think, came in 1980s. There was Ramakrishnan, someone who got Nobel Prize, and so on. So, figuring out structure is very difficult thing. Sometimes X-ray diffraction may not measure hydrogen, so you have to use NMR, for example, right. So, if you can do all of that, then you can characterize the positions of the atoms, and you can see what is the repeat unit, called lattice constant. And once you have this gives you something called initial structure, atomic position and lattice parameter. These are the inputs or ingredients for DFT calculation. Now, this atomic, as I said, the atomic position can come from X-ray diffraction, NMR, and nowadays there are many databases like crystallography open database, Jarvis DFT is one I made, materials project, and so on. And again, there can be primitive structures, conventional structures. So, suppose you want to represent aluminum. Can anybody tell me what's the number of atoms in a primitive cell of aluminum? 2. Who said 1? 1. Anyone else? You are right, 1. In aluminum FCC you do only 1. For silicon there are 2. For silicon, yes, primitive cell. So, again, you don't have to remember this, but it's a good things to know, like how many numbers of atom in the primitive cell, and luckily all these database kind of give you this information. You don't have to remember this. You just go to the database, click on aluminum, or I don't know, aluminum carbon, and it gives you something called CIF file or POSCAR files, and then you use that as an input to DFT calculation. So, here are for example for aluminum, silicon, gallium arsenide. These are very popular materials in material science, and these are some of the structures. Now, once you have the structures and you want to solve this, remember we have to do the grid on which this equation will be solved, and we have to expand the wave function. The wave function is not analytical quantity like psi equals to e to power I k r. It's not like this. You have to put on a grid, right. So, this is why we need something called basis set. Now, this basis set can have different types like localized orbitals, plane wave basis. So, localized orbitals are more popular for molecules where things do not kind of talk to each other or not periodic, but in materials like aluminum, silicon, things are really can be represented as a small unit cell that can be repeated multiple times to generate the entire infinite crystal, and for that we use plane waves. I'm sorry. So, yes, so localized orbitals was mostly used for molecules, while plane waves are used for crystals. But what do you have both molecules and crystals? Any guess what we should use? Like suppose you have a system where there is a surface like gold surface, and there is a molecule like methylene. So, what should we use, plane wave basis or localized wave, basis set? Plane wave. Why? Because still the bottleneck is this crystal structure, the periodic part, right. So, again sometimes they are mixed behavior, depends on the system you are modeling, you have to choose in one versus other. Most of the DFT code that we have been using is based on plane waves. Why they are popular? Because the Fourier transform, right. So, Fourier transform is extremely fascinating method that makes things go very faster. If you want to do integration, like e2 per ikr, you want to just integrate or differentiate, the k is just either over or just multiplied by it, differentiation. That makes things really faster for when you try to solve a material science application. I won't go too much details of this, but I do want to point out these things called lattice vectors, A1, A2, A3. You see there's a vector sign there, because the crystal like this thing is represented by A vector, the V vector and the C vector, or A1, A2 and A3, right. So this is not a number, it also have a directions. So this A1 has 3 numbers, A2 has 3 numbers in XY, XYZ, and A3 has 3 numbers, and that's how you represent something in 3D. Now if you want to do Fourier transform, you have to work in reciprocal space. So you have to do something called B1, B2, B vector, which is kind of counterpart of the real space called A1, A2, A3, and you take A2 cross A3 over the volume or something like this, and you get the G vectors which satisfy this equation. Luckily, in our age we don't have to code all of this. This is already implemented in software like VAS, Conespresso, and so on. So but it's good to know these kind of things a priori. Now another important things in DFT is pseudo potentials, which is kind of, when you remember we talked about there are k electrons, l electron, m electrons, and some of them are very sharp, they are very tightly bound near the core, but if you go away from the nucleus they are kind of loosely bound. So if you want to represent by one function, it's like very highly peak here and then it's very short peak here, and mathematically it's very difficult to represent this kind of function, which is very localized at certain point and very delocalized in one. So what we do is something called pseudo function, where instead of taking this highly variable thing, we make a kind of approximate function like this, and that's called pseudo function, and that's also give rise to called pseudo potential. Now this pseudo potential can be of different types, called norm conserving, ultra soft pseudo potential, and projected augmented wave. We mostly use projected augmented wave because of numerical efficiency with Fourier transform. So but I think some of the software like Conespresso only allow norm conserving. For some they use project augmented wave too. It's good to know this. Now depending on how much budget you have to solve a problem, like, and how much computational power you have, you might be choosing one software versus other. For example, VASP is a commercial software, others are not, so they are publicly available, but for one reason or other, VASP seem to be very popular, and somebody was telling me out of all the HPC resources, 30% or something goes just for running VASP of the entire world computational power. I heard that, Instagram, right? So when Instagram is not being used, all the servers are being used for running DFT calculations. It's so much used, like calculating different amount of data. The Google, I heard that all the YouTube servers, Gmail servers, they, whenever there was a free time, they wrote a script, kind of whenever there's a free time, create a new atomic structure, calculate properties, and make a database. And they created like a few million materials. Genome, yes. I forgot how many millions of material they created. 2 million or something, crazy amount of material. So as a researcher, like at IIT and stuff, we can't even think doing that much amount of calculus in a few months. But yeah, so what I want to say is like DFT is probably one of the highly used software, not just for material science, but literally for computation in general. And there is a quote I heard that how all this model like Cloud and ChatGPT have kind of eaten all the data over internet. There's no data left. So what's the new data? Physics is the new data. So the physics doesn't have ending. You can from periodic table create enormous amount of combination of materials and keep learning this. So that's what they are doing. So can you guess, if you have 100 elements, how many materials can you make from periodic table? Any rough guess? Remember permutation, combination, and all these kind of things? You have 100 elements from periodic table. How many materials can you make? 100 C4, that's right. But remember, it can be repeated too. Here there's a combination. There can be permutation, but there's also repeat. Remember the permutation combination will repeat things. Think about that.
And polytypes also we can consider same composition for all other types.
Sorry, say it again.
101 minus
Which one?
101 power 100 minus
101 power 100 minus 1. Yeah. So let me break it down. Suppose you have combination of two elements, then it's 2 to power 100 because they can be repeated, right? If you have 10 element combination, you can have 10 to power 100. Like so Meta and Google can go forever running this simulation, and they still have a lot of data to share, right? So this is the status. Again, because we did not know this damn exchange correlation, we need all this Instagram and YouTube computers to solve this problem, right? So again, there are some research work because there is no analytical formula. Maybe we can use the machine learning to come up with something more sophisticated and more faster and stuff like this.
So once TikTok is banned, you'll have more space.
Hopefully. So remember, you are still dealing with few atoms like aluminum, silicon, but the huge field of like proteins, macromolecules, and stuff like this. We don't even touch that too much, but some of that can go in there as well because there can be multiple repeats. So it's not just 10 to the power 100. It's like, I don't know, countably infinite or whatever the word they call it, uncountably infinite. And remember, there was a classification of infinites. Anyways, so once you solve a quantum equation, what do you get out of this? First thing we get, remember from the quantum equation, electron density of states, electron density of states, which is basically in each electron volt bin how many states of electrons are there. Optimized lattice constant. So suppose we know the lattice constant I know the lattice constant of aluminum is 4.05 angstrom. But what if I have aluminum, carbon, nickels? What's the optimized lattice constant? We don't know this. So we throw this into DFT, let it optimize, and we get the optimized lattice constant. Why do you need that? Because based on the structure property performance relationship and so on. Stress strain curve. So example, this you can get stress strain curve. Excuse me. Bulk modulus, thermal conductivity, magnetic moment, and literally theoretically anything you can think of, because we have wave functions. Unfortunately, there have been not too much machine learning or for wave functions. So I asked one of my students to do that, and she has not done it yet, but it's a very difficult problem to solve. But if somebody can do machine learning for wave function, I think it will be truly fascinating in a more manageable way, because wave functions are very challenging quantity, huge quantity, right? Anyways, so as I said, there are many databases out there which uses crystallographic information and DFT put together and made a huge database. So one of them is called Jarvis DFT, which comes with the periodic tables. For example, you can click on certain elements that you are looking for, like aluminum and oxygen, or here it is molybdenum and sulfur, and it gives you, for example, the identifier, what the material, we give just an arbitrary identifier. The formula, it can be MOS2, MOS, MO3S2, whatever combination, space group number, crystal system, formation energy, band gap, bulk modulus, so many properties calculated from this. So it took us I think 7 years to do, I think 100,000 materials, which I think again the focus was we converge all the K points, converge cutoff. We don't do just optimization of energy, but calculate many properties like solar cell efficiency, thermoelectric property. That's why you get less number of materials but more data. Sometimes this is also a good sign of versatility of data. You don't have the same thing over and over, but something more useful as well in your data set. In Jarvis DFT, for example, we have this functional called van der Waal DFT opt BT8, TBMBJ. Don't worry about the acronyms too much, but these are certain flavors of the exchange correlation, and certain 80,000 materials, 1700 elastic tensor, and so on. These are some statistics. We have some superconductor transition temperature and so on, Raman spectra, so on, and these are useful for multiple material design. And once I remember as a postdoc, which was 2015 ending, yeah. So I graduated in 2015. From 2016, for 2 years I did not have any papers, 1.5 years. I was just making the infrastructure for like how to automate everything, so that I click a button, it submits the job, do the calculation, do the post processing, make the website, put the website already, make it interactive, everything in one pipeline. So it took 1.5 years. But once it's done, now I'm here and thousands of codes are running day and night from many materials, and that's the power of automation and programming. And again, you give this data to different postdocs. They use their technique, like, okay, maybe this solar efficiency, I want high solar efficiency, high mechanical properties, filter it out, find a discover new material, experimentally synthesize it. That's the paper, right? And I know many researchers who do this kind of filtering kind of things, and it becomes a paper machine kind of, right? And not just a regular paper, all of them are Nature, Science, and all these kind of things. So you can really produce high quality paper from this, especially when you have validation with experiment. So there are several papers from this. Okay, so how are you doing with this time? We have still 15 minutes to bore you. So we talked about quantum mechanical principle. How about classical mechanics? Usually people do the reverse way. So first classical and quantum. I try to intimidate people first with quantum mechanics, so and then go with classical. So in classical mechanics, we have seen this Newton's law, force proportional to acceleration, where the m is the proportionally constant. We have seen this over and over and over. But when we talk with atoms, right, how do you calculate forces, right? So force comes from the derivative of potential. We don't know the potential. What should be the form of that potential? There have been certain attempts to come with classical potential, kind of manual fitting and stuff. And recently there have been several Nature papers on how to get this form into machine learning way. Like I don't need to know the form of the potential. Just I'll give you the weights and biases, and from there I can give you potential. You take a derivative, you get forces. Once you get the forces, you can integrate this to get what happens at time t0, time t1, and can evolve a system over time under pressure, temperature, compression, tension, and so on. So you can kind of model any kind of behavior, and that's really a huge field of research. So F equals to ml looks very simple equation, but underneath there is more complication to this, and it's used for not just for material science, for planetary motion. I was reading an article, a funny thing, side story, that it came from India somewhere. It was somehow Manchester University or some Cambridge University. They said that Newton kind of got this idea from India, which is kind of debatable topic, but it's interesting if you want to fun to read about this kind of things like me. Anyways, so molecular dynamics. Here's a nice little image or video on the right hand side, where we are trying to simulate a single crystal aluminum loaded in this 100 plane and straining it, how the atoms move. Now think of it, all the atoms kind of are all of the atoms are linked to each other, and we are trying this complicated equation, and we cannot do it analytically. That's why you need computational research or computational power, and that is done with this molecular dynamics, and this was first kind of given by this guy called Elder. Again, I had a chance to meet with Elder, who showed this phase diagram of Hart spheres, and the basic idea is you solve Newton equation of motions for individual particle like atoms and ion, and interactions are approximated by a thing called classical model potential or force fields. I was teaching force field in one of the course, and they think this is a movie like force field or something, but make sure it is. I think there is a movie for this, but what the point I'm trying to make here is this force field is a very interesting area of research, and people who work on this are, I feel like they try to solve one of the toughest problem in science, because again there is no unified theory of how atoms talk to each other or interact with each other, and these people are trying to do it in analytical theory or machine learning and so on. But this force field or model potentials is what we need for running a molecular dynamics calculations. Yes, all right. So let me see if this one works. Nothing works. So in a MD simulation, again you need initial atoms, initial masses of the atoms. The forces initially 0, there is no forces first, and then you assign the momentum and boundary conditions, so that if you have a chunk of aluminum, you are pushing it. After this atom, it again comes back and it wraps to each other, and this is called periodic boundary conditions, where instead of modeling infinite system, you try to model a certain repeat unit, which can be after a certain point come back to this from right to left or so on, or left to right. So, these periodic boundary conditions are very important, and we solve this F equals to m a, and from this we get the r, which is the position at time t, and we solve this to get to predict future or predict fast or something, and we calculate the energy, we calculate the forces, we calculate the trajectory, which is the time evolution of these particles. And unfortunately, this movie is not working, but it's basically show you how, if you have a rod or something, how you pull it, how the atoms will behave. And so, yeah, force field or interatomic potential have different types. So, one of the most common one is Lennard-Jones potential. Any of you have not heard of Lennard-Jones potential? Don't worry, there is no shame in this. So, Lennard-Jones is probably one of the most primitive, but still very influential interatomic potential, where you have two atoms like argon gas or something. Then there is a equilibrium point where they are kind of they are happy together, right. So, that is called equilibrium length. So, this equilibrium bond length here, where the energy is minimum. Remember, energy is minimum. You pull them to apart, where the r is increasing, it also gives the energy goes up, or if you put them together, the energy release goes up at 1 to the power r12, right. So, again this is modeling a simple 2 atom system in Lennard-Jones, but beyond Lennard-Jones there have been many different formalism, because there is not just 2 body, there is 3 body, 4 body. So, many body potential like MEM, EAM, Torsov potential, bonded potential, where there is a spring constant kind of thing. So, people try to come with different kind of idea how atoms talk to each other, because nobody have like unified theory again. So, they are like you can take 2 atom interaction, angle interaction, dihedral interaction, improper electrostatics, where not just bonding, but also the charges, van der Waals bonding and so on. And these are list of several machine learning force field formalism that is used for protein modeling like CHARM, AMBER, and some of these are commercial, they make ton of money just selling force field. I know there are some certain companies where employees full time job is to develop a customized force field for a particular drug or medicine or material, and they are paid a huge amount of money just for that. So, this is a good business if you want to be an entrepreneur, one of the ideas, and there are many formalism. So, yeah, this is Bernie Elder, and he was the first guy to kind of convert this F equals to m a to actually solve for realistic material, right. And as I said, there are many type of potential like Coulomb potential, Lennard-Jones potential. These potential lack angular information, there is no 3 body interaction. Then there is Stillinger-Weber, I think EAM, bond order, and these potential lacks charge information. So, we have fixed charge potential like Coulomb Buckingham, other force field like reacts COM, which have modified charge. So, again not just charges, you might have magnetic moment, right, which is also important, spin orbit coupling and so on. So, it can be more and more sophisticated, this kind of force fields. So, similar to Jarvis DFT, there is something called Jarvis FF, where you select a certain element like aluminum, it shows you all the force field that are available, and not just Jarvis FF, there are other repositories like IPR and GROMACS, which also have a collection of force fields. And as I said, some of the companies actually sell them, like I think Schrodinger has some part which just sells interatomic potential. Now, that is fine. I do want to point out about statistical ensemble. So, it's what is statistical ensemble? It's like real world experiments often under certain specific conditions like constant temperature, constant volume, constant pressure, and there are various averaging techniques, you can call it, or hypothetical copies which are used for solving this molecular dynamics, which are like here I said averaging over all microstates. So, for example, if you want to simulate under constant number of particles. So, there is a chunk of material where the particles are not escaping, constant volume and constant energy, there can have the number of particles are same, volume is same, but energy might change, but I want to keep the temperature fixed, that is NVT. You might have number of particles might be going like outside the system, volume is fixed, temperature is fixed, that is mu Vt, and similarly NPT. NPT is the toughest simulation, but more realistic, but many systems actually fail doing NPT because the system becomes unmanageable. So, most of the simulation follow NVT, barely NVE simulations. So one of the ways to solve, as I said, we have quantum mechanical and molecular dynamics. So one of the idea for drug design by this guy Martin Karplus from Austria, he proposed, why don't we make a hybrid approach, right? So for part you really want to focus on, I will do quantum mechanical modeling. For rest I will do molecular mechanical modeling, but the problem is how to deal with the boundaries of these two regimes, and he proposed some ideas for this. That is one way to solve this. Another way to solve is machine learning force field. So one of the paper here I highlight you called unified graph neural force field, and there are many variety of this. The idea is you can take any combination of periodic table elements out of 10 to the power 100 or anything, and it should be able to kind of model it in a way, in a more generalized way. So there have been so much research about this kind of work. So again here we have to choose the right software. So there are LAMMPS, GROMACS, AMBER, OpenMM and CHARM. It depends, for example, you are dealing with solids, you will be probably dealing with LAMMPS. If you are dealing with macromolecules, polymers, proteins, you will be probably dealing with CHARM. There have, okay, I don't know what I did. Anyways, so there have been certain attempts where just one framework can do all of that, and that is also an area of research. Okay, so last part is the continuum mechanics. How many of you have done finite element modeling? Please raise your hand. Just 1, 2, 3, 4. So finite element modeling is also a very popular technique, especially for dealing with large systems, not just at atomic level, but actually realistic millimeter, centimeter scale. And finite element is a part of a method called continuum mechanics. Continuum because this is a continuous shape, continuous material, not just atom by atom. And in continuum mechanics, it deals with elasticity, plasticity, viscoelasticity, and it guided by the conservation of mass, conservation of momentum, conservation of energy, these kind of theorems. And they have application is like state strain behavior, temperature behavior. Is very popular in civil and aerospace and mechanical engineering. So it was proposed by this guy Ray William Clough, and the idea is you deal with finite sizes where you take a sample and break it down into finite pieces called nodes, and you try to solve this using partial differential equation using a software like ANSYS. I think Phi can be used, Phoenix can be used. There are many software. Again, we won't touch too much of finite element, but I just want to point it out. So foundation of finite element method. This is weird. I don't know. Once you have the periodic boundary conditions and you can represent a partial differential equation like Poisson equation or heat equation in a form of y or Ku equals to F, where K is material property, U is the behavior like stress, strain and stuff, and F is the action applied, then you can simply do U equals to K inverse F. Matrix inversion, remember linear algebra? Although it sounds very simple, there is a lot of numerics for this, especially if you have thousands and millions of nodes, how to do it more efficiently. And if you can solve this, it can be used for mechanical, civil, fluid flow, electromagnetics, solid mechanics, biomechanics and stuff applications. Again, I will not go too much in the finite element method, but it can be useful for elastic calculations, thermal, fluid, electrostatic modeling and so on. So the idea is, in an ideal world, we can do both quantum mechanical, classical mechanical, finite element in one picture. But of course, things are not that simple. Sometimes you have to solve from one and pass the information from one model to another model and solve that and so on, especially if you are working as an engineer and so on.